Thank you for kind introduction. So it is a great pleasure for me to, and great honor for me to receive the award. Great pleasure to share with you a part of my research. So actually today I will try to bring you to the work of gas sorption by clay. And first of all, well, we need to know why do we need to study gas sorption? There have been two main contexts historically, so shale gas and carbon sequestration. So actually, in shale, it has been estimated that up to 80% of gas can exist in adsorbed phase. So for this reason, it is very important to understand not only the porosity of shale, but also their gas absorption capacity to properly evaluate the capacity of the reservoirs. A new context which has emerged since a dozen of years is nuclear waste repository. Actually, it turns out that several radionuclides like carbon-14 can exist in gaseous phase, so in form of methane or CO2, for example. And for nuclear waste management agency like ANDRA in France, it is important to take into account the transfer of this gaseous issues in Bulgaria. So the topic of gas sorption by place is quite old, but so data is quite abundant, but in many cases people rely on mineralogical properties of place to interpret adsorption, while textual characteristics are not always taken into account. And in our approach, we try to explain the observed picture of adsorption relying on texture and many other forms of materials. So to make you familiar with this topic, I will introduce you the mechanism of gas absorption by dry place, and then we will move to water containment systems. Okay, so as I told you, textual properties is a very important criteria to interpret absorption. So there are several textual properties. The most common one is surface area and microporosity. Actually, surface area of place, as you know, can be determined theoretically using this formula, where we take into account the dimensions of ferrosilicate sheets, density of the mineral, and the number of sheets stacked within the particle. And this characteristic ranges between a few dozen square meters per gram for natural place, and it can reach several hundred square meters per gram for synthetic nanoclays. So this formula actually allows to calculate surface area only in case of perfectly ordered arrangement of particles. But we know that in real life, so-called two-precipitation can take place, which result in the appearance of microporosity on the edges of the particle. And so the surface area measured by absorption or gas absorption is usually higher than the geometrical surface area, which we can determine with this formula. Okay, the next factor is so-called aspect ratio. As you know, on the surfaces of clay, we can find edges and basal faces. And from a structural point of view, these elements are very different. So basal faces mostly contain SC or SC bridges, so silicon bridges, trigonal cavities, and tiles. While on the edges, we find orange groups. The last aspect is called interlayer porosity. So as you know, interlayer space of square glaze is accessible to water, but several gases can also penetrate in the interlayer space, and I will show you in the next examples how it impacts the absorption capacity. Okay, so let's focus on the first control, so surface area. So here we can see the isotherm of methane absorption by monomer line, and almost all the isotherms of gas absorption by place look similar. So we have pressure, amount absorbed, and kind of curve which is ideal. Literature on this topic is quite rich, and we can find quite many data. And actually, for methane and CO2, we can find a linear correlation between amount absorbed and the surface area. From the slopes of these lines at a given pressure, at 10 bar, for example, we can determine that the affinity that clays absorb 4 times more CO2 than methane, which is usually found for many other porous materials. What is curious about the systems is that the correlation is not strict, it's not perfect. which means that different clays may have different affinity to gas. And if we divide the adsorbed amount by the surface area and we separate clays into different classes, we may find that for smectites, the affinity can be high or low, so quite largely distributed, but for elytes and kaolinites, it is rather low. To understand the origin of this difference, we carried out an experimental study on 4 model clays. So 2 elytes, elite 3 from France, IMT2 from USA, and montmorillonite obtained from QEBF, exchanged with sodium and with calcium. So these clays were characterized by nitrogen absorption to get surface area, by XRD to verify the purity, and we have taken a few photos for the article. To measure gas absorption isotopes, methane and CO2, we used this setup, which has the same principle as DET analyzers, but we proceeded manually. So pulse opened manually. And we measured isotopes. So here we see methane, CO2, so smectites and elytes. So now, if we calculate the absorption with respect to the surface area, we end up with the superposition, with perfect superposition of the isotopes for smectite and for elyte. And actually, you can see that our here will reach the same level, but for smectite, the filling of this capacity is faster than for elytes. So we can say that smectites have higher affinity to gas. And the same trend has been found in the literature. So smectites can show higher affinity than elytes. So to understand, to explain this behavior, we tried to rely on the structural difference between clays, so mainly the charge. According to the literature, we know, so from atomistic simulations, we know that if we compare pyrophilite surface without cations with monomerilinite surface, which contains some cations, actually there is no difference for methane absorption, but in case of CO2, cations do promote the absorption of this gas. In our series, we have actually the increasing number of cations when we go from calcium monomerilinite to sodium elyite. So we should expect no difference between methane absorption isotope for all these clays, and should expect higher absorption or higher affinity for elyite clays. But this is not the case. Elyite have lower affinity than smectites. So relying on structural difference, we cannot explain the observed trend. So let's see what we can get from texture. And under texture, I will say we will use aspect ratio. Okay, so to access to the aspect ratio, there are several techniques. IFM, maybe transmission electron microscopy image analysis, but also techniques based on gas absorption. So the most known one is called derivative isotope selection. So this technique has been invented in early 90s by a French group of mineralogists in Nancy under supervision of Villeras. So in principle is relatively simple. We will measure a high resolution isotherm with a high number of points low pressure. And then when we pass to the logarithmic scale, we can see that actually we have several contributions from the isotope, which can be better highlighted at when we pass to the derivative. Yeah, so we can see peaks. And actually, because the edges have higher absorption energy, they usually absorb first molecules, and then the absorption takes place on the basal spaces. So with this technique, we can differentiate edges and basal spaces. And if we model this isotope with well-known theoretical equations like BET or its modifications, we can perfectly fit the profile. And what is important, to get access to the contribution of each surface domain to the total surface area of the clays. So here is our result. So 2 monomerilinite, sodium and calcium, and 2 elyite. So first 2 components are assigned to the absorption on edges and the two remaining components at higher pressure correspond to the adsorption on basal plate. And what we can see here, that if we compare smegmites with elite, the component at lower pressure, which corresponds to basal to edges, is much more pronounced, which means that the fraction of edges in the total surface area is higher in this place. And actually, for both elite, it is on the order of 20%, while for smegmites, we are between 40 and 45%. So now it is not surprising that for smegmite, we have higher affinity. This is because we have higher amounts of high energy surface site on this side. So let's have a look on another mechanism of adsorption, which is related to the intercalation of gases in the interlace. By the way, a very good talk was given by Peter Zimnowski on Tuesday on this topic. So in this example, we take two plates, two smegmites, two monomelonites, one exchange with sodium and one with magnesium. If we dry this place, for smegmite, complete removal, for sodium form, complete removal of water at about 100 degrees. Magnesium, actually, we need to heat at higher temperature because water is strongly soaked from this cation to completely dehydrate the sample. And actually, if we do extra diffraction on the first peak, we see that starting from 115 for sodium, the structure is completely collapsed. But for magnesium, we need really to reach very high temperature to attain the same interlayer space as for completely dry smegmite. And so if we measure methane and CO2 adsorption isotherms on completely dry place, so for sodium dried at 115 and for magnesium dried at 200, we obtain kind of the same isotherms. But if we do the same for magnesium smegmite dried at 115, which still contains some water in the interlayer, we end up with much higher adsorption due to the incorporation of gas molecules in the interlayer space. So actually, the mechanism is schematically shown here. So on this slide, we start touching the problem of gas absorption in presence of glaze. And now I introduce you the second part of my talk, which will be the effect of water on gas absorption. So just to make you familiar with the topic, I will show you a few isotherms from literature. So here we have CO2 adsorption isotherms by zeolite and CMF, which is carbon material, so activated carbon. So isotherms look exactly the same. The only difference, is in capacity is due to higher surface area of zeolite. However, if we measure the water adsorption isotherm on both materials, for zeolite, micropropylene with water has a very, very low humidity, while for CMS, we need to reach 60% to start filling the post. And this is mainly because of its high hydrophobicity. And now, if we measure the adsorption of CO2 by humidity equilibrated materials in comparison to dry material at 1 bar, what we can see is that zeolite, even at low relative humidity, loses almost all its adsorption capacity. But for CMS, we need to reach very high relative humidity to start seeing the depression of adsorption capacity. So from this, we can learn that not the relative humidity is the main factor, but the amount of water contained in the sample. Well, in several cases, right, exotic cases, the pre-adsorption of water can promote the adsorption of other gases. So we may cite, for example, the formation of gas hydrates in porous media at the temperature close to 0 Celsius. And sure, the case of glaze, where water opens into their space, and so more surface will be available for absorption of gas. But in almost 90% of cases, when we are dealing with water, usually we lose from 70 to 99% of absorption capacity. And if in the lab we measure the blue curve, so nice isotherm for dry samples, in the nature, place can be moist and hydrated. And so equilibrium will be described with the bottom isotope. And so to understand what happens in presence of water, we first carried out experiments on model porous media. So we took two silica, so very filled and SBF15, so which were characterized by nitrogen absorption, and using some modeling, we could get the distribution of pore size. So SBF15 has very narrow pores, and the fill have larger pores, which are more distributed in the case of SBF15. So the silica were calibrated at 97% relative humidity in the desiccator, and by TGA we measured water content in the samples. And actually, a perfect agreement between water content from TGA and pore volume from absorption measurement signifies that under these conditions, both media are saturated with water. So using the same equipment, we measured methane and CO2 isotopes for dry and saturated materials. And as you can see, both solids lose almost 90% of their absorption capacity. So how can we interpret these isotopes? We can try to attribute the amount of gas absorbed not to the mass of dry solid, but to the amount of water contained in the solid. And going to the logarithmic scale, millimoles per milliliter, and a function of pressure, we will obtain linear plots. And in this scale, we can compare the uptake with the solubility of gases in both water, which we can find in literature. And what we can see is that in case of the refill, which is sky blue, we may realize that the solution explains pretty well the uptake of gas. While in case of SBF15, which has narrow pores, we are absorbed more gases than solubility allows, and the effect is more pronounced in case of methane. So this phenomenon is not new; it has been observed over the past decade, and it was called oversolubility. Actually, there are two possible mechanisms of this phenomenon. According to the first mechanism, water in close proximity to the surface is structured, and so it better dissolves gases. And according to the second theory, water is exactly the same in the four-pore body, but molecules in close proximity to the surface interact with the surface, which promotes the dissolution. In any case, whatever the mechanism, in case of material with narrow pores, this area close to pore wall is, let's say, its contribution to the whole pore volume is higher. So we will observe some effect in narrow pore material. So next, we characterize using the same approach model pore clays. So model clays, purified elite and purified peptide exchange with sodium. So the same trend, the loss of absorption capacity when clays contain water. And if we do the same calculation, the same transformation, we realize that also in this case, the solution explains pretty well the uptake of gas. Let's try to explain why. Actually, in case of elite, it is easy to explain because we can see on nitrogen isotopes the hysteresis, which is shifted to high pressure, which means that it has significant mesoporous volume, and these mesopores are quite large. And if you remember, for the seal, which also has large pores, we didn't detect significant oversolubility. While in case of smectite, we don't have mesopores. So here, hysteresis is mainly due to kind of non-rigid structure of the pores. And also, we need to keep in mind that under saturation, this clay contains a significant part of water in interlayer, and this water is very highly confined. So from one side, we should expect a very high oversolubility because of high confinement of the water. On the other hand, we should remember that interlayer water has very high ionic, and the salinity of water decreases the solubility of water. So this interplay between two antagonistic effects results in kind of low apparent oversolubility. But maybe in smectite clay with different layer charge, the behavior will be different. So finally, we got to clay rocks. So these clay rocks were provided by Andra, which is in charge of nuclear waste management in France. So they come from different depths, and to their main difference is that one of them is slightly higher spectate fraction content. So these places were characterized in finely ground and roughly crushed state. So nitrogen isotopes look exactly the same, which means that fine powder represents pretty good the microstructure of the broad rock. Yeah, you can also see that clays separated with water in powder state and crushed state have quite close amount of methane. So there is no difference between both states. Now, if we do the same transformation, we realize that in contrast to purified clays, which are shown here in gray and black, clay rock show significantly higher oversolubility of methane, but also CO2 to a lesser extent than model clays. So to explain why we have proposed one hypothesis. Actually, yeah. Just before I go to interpretation, we also compared our data with literature. So we found some data for shale, which is also characterized by low organic carbon content, like our place from our study, and also one monazite from this water. And as you can see here, we find very good, coherence with our result. So to explain the observed trend, we propose the following hypothesis. Actually, for purified clays, mechanical constraints have been released because they were disaggregated in water. So when purified clays absorb water, they can swell the exterior. So particle can expand. While if we take clay rock, actually it contains nanocrystalline calcite and silica, but also it keeps mechanical constraints required during genesis. And when swelling fraction uptake water and swells in the system, it constrains the available mesopores. And probably it results in significant narrowing of micropores and mesopores, which results in higher oversolubility of gases. And now I move to conclusion. So on this slide, you can see all systems studied in this work. So we can see that for CO2, in most of cases, the solubility explains pretty well the uptake in presence of water. While for methane, in several cases, which are material with large pore sizes, solubility can also explain the uptake, but for systems with narrow pore sizes, the uptake is much higher than the solubility would allow. So why do we observe this effect only for methane? Actually, for this, we need to compare adsorption and dissolution isotopes. So on, let's say, on silica surface and in water. If we try to superimpose both isotherms, well, it is quite difficult to do because they don't have similar shape. But if you try to superimpose the isotherms, what we see is that adsorption of methane is much higher than its solubility. Yeah. So if we have the possibility, if methane have the possibility to be adsorbed on the surface in addition to dissolution, it will dramatically increase its amount in pore, which will result in apparently high oversolubility.